I want to be talking about the transmission of touch, a multimodal wearable controller for tactile haptic feedback for the transmission of touch. So that's a lot to unpack. So just like when we first unpacked the VR kit, we had our VR headset as well as these VR wands or these controllers. And one of the things that we were able to do is we had this idea with a lot of gaming sets that we have this associative control with these controllers and that we as the user conform to the controlling device. This is very awkward and unrealistic. So an example here that I'm showing is when I'm able to pick up a VR object, I push a button that I associate with the function of grabbing an object. And then when I release it, when I throw the object, I release the button and the object propels and carries that momentum. So this is the first example where this is not how we naturally grab things in real life. What we do is we go and we grab an object with our hands. That is the most dexterous and optimal way of us engaging with objects. And this has the effect of diminishing the educational value in VR training simulations, where what you do in the VR training simulation should map as realistically and as immersively as possible to the real world scenario, so that what you learn, the value you gain in the VR training simulation can be translated into the real world and have that sort of value. So the second scenario we found ourselves is we have a small playing area. However, if we want to run across the room, we're limited by the VR playing area set up by the HTC Vive. So to overcome that, our little sandbox demo allows us to push a button, again, an associative control, and allows us to teleport from place to place. And again, we are able to interact with our environment. This, as awesome and interesting as it is to be able to move around, is again an awkward control or a way for us to associate a button press with an actual action. Normally we would just walk over. Of course, with the given VR setup, we are restricted in this way. The final scenario I found myself was as I was teleporting around, I found myself happening onto a table, and as I was standing on the edge, this is where I thought current VR technology did very well. I was standing on the edge and I was looking over the table, and although I only knew it was a couple feet to fall to the ground, the idea that the visual feedback that I was receiving from the simulation told me that if I did take a step and I would fall. And this was the immersion that gave me a gut feeling that, you know, I was scared of heights, even though a few feet isn't bad, but the idea is it created a physical reflex from a virtual stimulus. So I was able to step off and nothing happened, and I just took a step forward and fell down in the VR simulation with no consequence. This again kind of diminishes the value from the immersion inside a VR simulation. And the last scenario I have for you guys is when you have one of these controllers and you go up to a VR surface or a wall, for example, and when you go to touch the wall, you expect when you touch a wall in the real life that Newton's third law will act upon you as you act upon the wall. And however, with the VR controllers, you're able to just move through the wall and there's no any sort of haptic feedback or cue to let you know that you're engaging with the wall or impede your feedback. So again, this was the immersion breaking aspect of the VR technology today. And so what we decided to do in the Lacomi lab was to seek to improve the immersive experience in a VR simulation, as well as bring more realism to VR simulations as well, so that users, when they do their training in their VR simulations, these best map to real life scenarios in which what you learn in the VR simulation is valuable in the real world. And so our metric to determine whether we were successful or not was to be able to generate a physical reflex from a virtual stimulus. So next, we're going to start talking about some of the applications and some of the current approaches that have been done in this field, and then we'll talk about our solution that we have made to take one step further into making this more of a reality. So first, we have medical, and I kind of touched upon this a little bit already. So this is a great example for surgeons in training to practice in a safe and non-consequential environment. However, it's still important for them to practice in such a way that it is as real or as approximately real as it's going to be in the real situation, so that they're best prepared to do it, and any high pressure scenario that we can create in the virtual space will map to the physical space. And this will best prepare our students. Furthermore, education. The way we learn in classrooms today hasn't changed in several years, and we believe that by incorporating haptics and VR technology that we can improve the educational value by learning through experience and developing intuition through experience versus learning about 3D concepts, for example, on 2D planes, as we do with chalkboards, whiteboards, and on paper. So There are two examples where the haptic paddle allows the user to engage with a physical object that gives kinesthetic feedback to the user so that they can better understand when they're tweaking parameters on Newtonian mechanics or second order systems, that they can feel it interacting with them and they can better understand how these concepts work. Furthermore, we can learn the 3D concepts that I just mentioned in a 3D space so that we can get a different perspective for how we learn and how we approach education. Finally, and probably the most prevalent, is entertainment. This is where we see VR technology really making headway and breaking into the consumer household with the HTC Vive, which is what we use in the Transmission of Touch project, as well as the Oculus Rift. There have been several devices made in the field where you can interact besides using these awkward controllers that at least try to approximate it to be a little more real. So the Haptics Link was a device that provided kinesthetic feedback between the hand. So for example, if you were pulling a bow and arrow, you can actually feel the tension increase as you pull it back, and when you release it, that tension disappears. Now this was another more realistic approach. However, still we, the user, are conforming to the controller when we believe the controller should be conforming to the user. So before we talk about some current approaches, we're first going to talk about how we classify different types of feedback. So first we have kinesthetic versus tactile feedback. Kinesthetic, this is what you feel in terms of the weight, size, and orientation of the object. This can also impede the user's motion, versus tactile feedback, where this is what you feel on the surface of the skin. So things like texture, temperature, vibration, and other things that you sense that can be distributed on the skin. Next, we separate our haptic devices in two different categories. That is a grounded system versus an ungrounded system. So a grounded system is a device that has some sort of reference point. That is that the user's motion can be impeded relative to a benchtop or the earth, versus an ungrounded system, which has usually a larger range of motion. However, it's unable to restrict the user's motion completely. Thus, we'll still be able to move through walls, unlike a kinesthetic feedback device where it can actually prevent your arm from moving if you're engaging with a VR object. So some of the current approaches include the Phantom. This is a very popular device that is referenced a lot. It's also a commercial device and used in a lot of research. This is a grounded system. It provides kinesthetic feedback, but it has a limited working area and it doesn't give you any tactile sensations. We have the Cybergrass, which is another kinesthetic device. This one is ungrounded, so you have a larger range of motion in which you can interact with your VR environment, and it provides force feedback on the fingers relative to the palm. Finally, we're going to talk about just lumping some tactile feedback wearables. So each of these, the CyberTouch, the UltraTouch, and the electrotactile glove, each provide one tactile sensation. So the CyberTouch provides vibrations in the fingertips, the UltraTouch provides temperature feedback at the fingertips, and the electrotactile glove actually provides small electrical current simulation throughout the entire glove itself. So all these are ungrounded systems. However, they have a large working area but provide no kinesthetic feedback. So our solution was to take some of these elements and put them all together. So we took the vibrotactile, the temperature, thermoelectrics, and the electrical current stimulation and put them all into one glove to make the Touch Glove, a comprehensive tactile experience. It's an ungrounded system, so we're still actually able to move through walls, but we believe that this takes one step further into bringing multiple senses and multiple forms of stimulus or multiple modes of stimulus into a single device. And because it is an ungrounded system, we have a large working area. We're not restricted to any sort of benchtop. All right, so the Touch Glove is part of the Transmission of Touch project as a whole. It is the main device and it is the controlling haptic device. It controls the robotic arm, which acts as our physical complement to the Touch Glove, and the virtual hand model or a virtual component, which is our virtual complement of the Touch Glove. Each of them provide a different form of stimulus, the robotic arm from the real life environment and the VR hand model from a virtual environment. So everything done with that is programmatic. So now we're going to talk about the Touch Glove. So here we have 5 flex-sensitive resistors, which act as our sensing device, so that when we bend the fingers of the Touch Glove, we can transmit this motion to the robotic arm or to the VR simulation. We have 3 tactile feedback devices, as we mentioned. We have 6 vibrotactile motors on each of the fingertips and 1 on the palm. We have 5 thermoelectrics, again on each of the fingertips, and we have 5 electrotactile devices on each of the fingertips. However, the way we've designed the Touch Glove is such that we can support up to 64 pixels, electrotactile pixels. Here's just a real life image, and I also have it here today so I can show you guys later or after. So when we were designing the Touch Glove, we broke it down into several subsystems. So the whole thing is powered by a 7.4 volt LiPo battery, and it goes through several voltage regulators to power the device. And then we have one input or sensing device, that is our flex sensitive resistor subsystem. And then we have 3 output subsystems. These are our actuators in the vibrotactile, thermoelectric, and electrotactile. So I'm going to talk about each of those systems and some of the challenges and solutions that we came up throughout the project. So first is our flex sensitive resistor driver. Here we had a flex sensitive resistor in a voltage divider configuration, and one of the problems that we faced here was that the output impedance of the voltage divider was too large for the microcontroller to sample quickly and provide clean readings, and it's important that we are able to sample as fast as possible so that we can create the least delay, the lowest latency possible when interfacing the touch glove to our virtual entities. So our solution here was to put an impedance buffer at the output such that the output of the impedance buffer provided the lower impedance that we needed to successfully sample clean readings and do this at a fast loop rate. Another problem we had in the microcontroller was that we only had a limited number of analog input pins. So to overcome this problem, we used an analog multiplexer so that we take all 5 of our flex sensors with their output or with their impedance buffer and feed them into one device. And we get one output pin that we can work with, and we can just switch between which one we're reading by multiplexing. Next, we have our vibrotactile driver. So here we have our vibrotactile, and each of them are driven by a MOSFET. This MOSFET is in a switch configuration such that when we PWM or provide a duty cycle at the gate, various duty cycles at the gate, we can control the intensity in which current flows through the vibrotactile, thus actuating it more or less intensely. Furthermore, we only have 5 PWM pins on the microcontroller, so to overcome this problem, we use a PWM driver. It has 16 channels, 6 of which go to the vibrotactile so that we can overcome our pin limitation. It communicates via I2C, and this is going to be useful because we use more than one PWM driver when we drive the electrotactiles, so this allows us to address each one individually, as I'll explain in more detail in a moment. The other 10 pins on this PWM driver, or other 10 channels, are used for our thermoelectric driver. So for our thermoelectric driver, we have a Peltier element on each of the fingertips, and one of the challenges that we had to overcome was that the face that's touching the user's skin had to both become hot and cold. So to overcome this, we use an H-bridge, which allows us to use one PWM pin to control the direction of current flow, hot or cold, and another pin to control the intensity of the current flow. So in this way, we can control the intensity of hot and cold and the direction, thus the face that touches the skin can get both hot and cold. Similarly, since these H-bridges each take 2 pins and it takes one H-bridge to drive one thermoelectric, we need 10 PWM pins. Again, this exceeds the number of available pins on the microcontroller. So the 10 pins are shared with the same PWM driver that we used with the vibrotactile. Finally, we have the electrotactile driver. This was one of the biggest design challenges that we had. The reason why is because to drive our electrotactile devices, we have to overcome the impedance of the skin. And in order for us to actuate each of the pixels, there was no commercial device on the market in which we can just do this all in one package. So we had to create it from the ground up. And the design requirements for this was to be able to achieve 100 volts peak to peak, a waveform in the shape of a square wave, and a frequency adjustable at the low end between 50 and 300 hertz. So in order to accomplish this, we have a 3-stage design. The first stage is our square wave oscillator. So at the output of this, we're able to generate our square wave. We had an adjustable frequency by using a potentiometer or a variable resistor. And the problem here is we had an output of 3.6 volts peak to peak, which is not high enough to overcome the impedance of the skin. Thus, we pass it into our second stage, which is our high voltage analog amplifier. And here at the output, we're able to select between 4 gain settings that we have set at 30, 50, 80, and 100 volts peak to peak. These are adjustable to some degree, depending on the resistors R1, R2, R3, and R4 that we choose here. And at the output here, we finally obtain the electrotactile signal in which we can simulate all the electrotactiles at the same time, so we can turn them all on or all off. However, we want to be able to address each electrotactile pixel individually, and the way we accomplished that was by creating our own multiplexer. So the way we did this is we created 4 sets of 16 relays. Each of these 16 relays corresponded to one PWM driver, and the way this works is that we put the electrotactile signal at the output of one of the relays, and this behaves as a switch that is open by default, and each of the outputs goes to each one of the 64 pixels. The input is driven by the PWM driver, so each of these pins connects to it. And when we send a high signal, we close the switch here, and we can actuate the electrotactile pixel. So with this, we're able to distribute our electrotactile signal to all 64 pixels of our electrotactile glove with the appropriate signal. So this can be seen here on one of our 2 PCBs. So we can see our 16 relays to our 1 PWM driver, and we have 4 sets, 2 on the top and 2 on the bottom, as well as we have some of our square wave oscillator circuitry and our high voltage amplifier. And this doesn't have the microcontroller. This is one of the 2 PCBs. This one stacks on top of our touch glove PCB. So our touch glove PCB is our main PCB. It has our microcontroller, our wireless antenna so that we can communicate with the robotic arm. And the design challenge here was that we had to separate or isolate our noisy circuitry with the vibrotactiles and most notably the thermoelectrics from our sensing and our quiet analog devices, which was our flex sensitive resistors. So that's why we kind of have them separated here. We have all the quiet circuitry on the right and all the noisy circuitry on the left close to the power supply. One of the problems we also faced was that the thermoelectrics demanded a lot of power. It's very inefficient to heat and cool the Peltier elements. And so we had to use a 3 amp regulator to power all 5 of our thermoelectrics up simultaneously. And this generated a lot of heat. So the way we overcame this was we have a 4-layer board design with several ground planes underneath the voltage regulator, and they're all stitched together via thermal vias to help dissipate the heat. So besides hardware, there was a large programming aspect that we took with the transistor touch project, and most notably with the touch glove. So when we were talking about our several different devices, we have 3 actuating devices, and they all share the PWM driver. So it made sense for us to make classes for each of the device so that it was easier to separate the complexity of the hardware from the application logic. Similarly, we use the PWM driver with the force sensitive resistor, and we will actually reuse these devices with the robotic arm, that is the multiplexer and the PWM driver. And the important aspect here was to have an object-oriented approach so that our code was more scalable, reusable, and more efficient. So next, we're going to talk about the robotic arm. Our robotic arm is a physical complement of the touch glove. It has 6 force-sensitive resistors, 1 on each of the fingers and 1 on the palm, that correspond to the vibrotactiles on the touch glove. Similarly, we have 5 thermoelectrics, again integrated on the fingertips, and these correspond to the thermoelectrics on the touch glove. One of the concepts that we tried to make prevalent here was the idea of mechanical biomimicry. So when our servos actuated the fingers of the robotic arm, we have 200-pound tensile thread running through the internal cutouts of the device. Similarly, to mimic nerves, we had really thin 30-gauge wire running to the fingertips to the devices integrated on the robotic arm fingertips. Here is our PCB for the robotic arm. We face the same design challenges with the robotic arm PCB as we did the touch glove. That is, we have our quiet analog sensing devices with our force sensitive resistors and our temperature sensors on the right, and we have our noisy circuitry in the form of our servos on the left. And again, these servos, when they actuate very quickly or against a heavy load, they generate a lot of heat. So we have a 5 volt, 5 amp regulator here. And again, this produces a lot of heat. So we use the same technique of making several ground planes on all 4 layers and stitching them with thermal vias to dissipate this heat efficiently. Again, the programming aspect here is also important in that we reuse the multiplexer with our temperature sensor and our force sensitive resistor on the robotic arm. And similarly, we reuse the PWM driver to control the servos of the robotic arm. So here is an example of our robotic arm in action. So you can see the touch glove is controlling the robotic arm, extending the fingers on the left. And then on the right, you can see the robotic arm actually grabbing an object. And when it does grab it, the vibrotactiles on the fingers actuate because they're touching the force sensitive resistors. Similarly, this device was actually at room temperature, but if it was hot or cold, the temperature sensor would pick that up and would actuate the thermoelectrics on the touch glove. So our final component is the virtual reality component, and this is the most exciting, I believe. We created a Unity game and created our own VR environment such that we use several scripts to simulate the robotic arm. So everything we do in the robotic arm, we do in the virtual simulation, as well as interact between the touch glove and our VR game. So the way we did this was we have several VR objects in the game that we can create, and we give each of these objects properties, special properties that allow us to do things like actuate the electrotactile, the thermoelectric, and the vibrotactiles. So to actually interact with objects, we needed an arm or a hand inside the game that mimicked our own, and we bought a Unity asset that was a hand and forearm. This hand has several joints in which map like our real fingers. We can bend each of these joints individually. In hindsight, one of the problems with our touch glove, however, is that the flex sensors only bend the bend continuously. If we bend it this way versus any other way, it all looks the same to the touch glove. However, to the virtual environment, we're able to control each of these joints. So the way we overcame this is that we just mapped the natural movement of the grabbing motion from the touch glove to each of the joints on the virtual hand model. So a future work here could be if we put flex sensors or strain sensors on each knuckle or on each joint, then we can actually keep the immersion more, improve the immersive experience by actually being able to bend each finger. Similarly with the wrist, we have something that tracks the motion of the arm, but it can't track the motion of the wrist. And one of my future works is to add something to be able to do the wrist action. So how do we actually engage and interact with these VR environments, and how do we get simulation to the touch glove? And the way we do this is our VR hand model has these colliders, these invisible spheres or other shaped devices on the fingertips. And when we actually go to touch an object, it'll trigger either a physical collision or it'll trigger a heat collision. And the way we do this is through our scripts or classes being the touch monitor, which actuates the vibrotactiles or the electrotactiles. And we have the heat monitor, which actuates the thermoelectrics. So I know it's kind of dark here, but you can see when the user touches this panel that we have given the property of cold, the user experiences the thermoelectrics actuating and getting cold. However, when we pull off of this panel, we do not feel the cool rushing through the thermoelectrics anymore. And this is an example of a device that has an emission distance of 0. It does not emit or radiate temperature or heat. Similarly, we have a device which is like a fire. And as you'd expect when you're at a fire, at the fringes of the fire, you expect that your fingers get warm, but they're not burning. And as you get closer and closer to the fire, it starts to get more intense. And we're able to map that appropriately. And what we did to make the immersive experience more realistic is that in a VR simulation, you feel safe, you can just go and touch a fire. If you do this in real life, it'll actually burn you. So what we did is, of course, we increased the intensity of the heat as you got closer, and then as you got very, very close, pretty much touching the flame, we actually zapped you with the electrotactile, so you can actually generate that physical reflex and actually feel like you're in an immersive experience where you know you shouldn't still touch fires even if you're in a non-consequential environment. Of course, no one was harmed in the making of this. Next, we have the method for which we track our arm when we're wearing the headset and we have our hand in front of us. We should be able to see a virtual arm that maps it appropriately. And the way we accomplish this is with the HTC Vive Tracker. So this is what we strap on our forearm, and we sync the VR arm to be as approximate to our real life arm's position as possible, so that when you have the HTC Vive headset on and you have your hand like this, you'll actually see the hand model in approximately the same position. And when you bend your fingers, you'll see the fingers bend as well, and it's supposed to feel as realistic as can be. So when our hand model actually interacts with devices such as this rock, if we make a small forced collision, the vibrotactiles will actuate gently. We would say this object is soft. And when we make a large forced collision against an object, we would feel the vibrotactiles actuate violently, and this would be an example of a hard object. We're able to give the rock and these panels these sort of properties. Next, we have the electrotactile actuation, and we actuated this when we performed the sliding movement or action. And so when we slide against an object that we gave the property of smooth, the electrotactiles would fire continuously to give the illusion that this is a smooth object. Similarly, for a rough object, if we gave the property the property of rough, then when we slid our fingers across it, then the electrotactiles would fire pulse or intermittently, such that to give the illusion that the object was rough. Finally, our touch glove needs to still be a controller. We're making the argument that this controlling device is conforming to the user, as it does in a wearable form. However, we still need to perform all the associative controls that we do with the device, with the controller, as we do with the touch glove. So remember again, the way we actually picked up an object was that we went to the object and we pushed the button to pick it up. So what we did with the touch glove is that when you have your hand and you go up near an object and you make a fist, you'll pick up the object and you'll feel the vibrotactiles actuate, and when you release your fingers or put them in extension, it'll drop the object or it'll carry the momentum if you try and throw it. Similarly, we needed to move around the area. Now there's no physical real life thing that allows us to teleport yet. So the way we approximated the pushing of the button and the creating of the ray and then moving to it is that we thought a gesture that made sense is when you actually point to tell someone to go over somewhere or to bring their attention there, is that when you would point your finger with your thumb sticking out, you would generate this ray, as you can see here, and when you close your thumb, you would actually move to that location, so you would move your play area, and that's how you would move around. Hopefully, we could achieve this in real life eventually, because that would be really fun, but this is how we overcame it in the virtual simulation. And of course, when you extend your fingers, you stop using the tool. So to make sure that this was truly immersive experience, we had to put ourselves to the test. And the way we did this is we had the entire environment, which I showed you guys in some of the images and the GIFs before, but we also created several training panels that had the property of smooth, rough, hot, cold, hard, and soft. And then we have both a training set in which the answers were hidden and a training set which kind of give hints. So hot and rough would have the red and the rough looking texture, so that we were able to interact with these devices and see if we can associate or feel the sensations and convince ourselves that it was a more immersive experience. And we believe that we were able to create these physical reflexes from virtual stimuli. So to wrap things up, the transmission of touch included the touch glove, our wearable tactile haptic controller that provided a comprehensive tactile experience in the form of the vibrotactiles, thermoelectrics, and electrotactile actuators. It gave us that concept of a more immersive experience when we were engaging in a VR simulation, and the VR simulation was our virtual complement of the touch glove. Similarly, we have our robotic arm, which is our physical complement of the touch glove, which provided us with physical stimulus and is an example of telerobotics. So the last thing I want to do is just wrap up with some things that I think would be really great to improve on in the future. So the first thing I would like to add is a Bluetooth to the touch glove. Right now with the HTC Vive, we already have a long wire that routes to the computer, so it made sense for us to just use a wire to also communicate from the touch glove to the computer. We could have made a separate node to communicate wirelessly, but it may have added more unnecessary latency. However, I believe the future of the HTC Vive, and I think the Oculus Rift already has wireless headsets, so it would make sense to add a Bluetooth so that you're completely mobile in the future. Next, in hindsight, the thermoelectrics were hard to control the exact temperature by controlling the PWM, so a really useful thing to do to modulate the temperature would be to add a thermistor or a temperature sensor on top of the thermoelectric, so you can do a control loop and control the temperature or regulate it. Finally, I was telling you guys about the wrist action. That was probably one of the most prevalent immersion breaking actions or gestures. So we would like to add a wrist action, but in the form of adding an IMU to the PCB. This would also allow us to do more advanced gestures like sliding down our finger and opening the menu and actually interacting with a HUD in the game. To incorporate or to support all of these and keep the latency low, we can add a 32-bit microcontroller. Really, the only benefit here is just more power to do more things. And the last thing that would be fun to explore is a flexible PCB. So I did design the touch glove PCB to be as small and as conformal to the user as possible. However, it might be fun or exciting to explore electronics that better conform the user in form of the flexible PCBs. So thank you for your guys' time, committee and guests. I'm happy to take any questions.